those nice T-shirts. Did they hand out these T-shirts of ITC? I think they're new because I haven't seen them yet. You all got one? No. He's special. That's another way of expressing it. Okay, before the break we looked at phenomena. After the break we look at how we represent them in a computer. And this is our list. Regular and irregular tessellations, points, lines, polygons, and triangulations. Let me give it a go. Let's say we want to represent a continuous field. Now we already identified that it's a field because it has a value everywhere and that it has gradual change. So every point has a unique different value. It's not like this whole area is agriculture. No, temperature changes in every direction. Now, we still want to store that in our computer. We want a way to represent continuous fields. And what you can say is that we can choose from either of two ways of doing that. What we could do is collect a huge number of samples. We can maybe put up a monitoring network for temperature, a lot of sensors, and then collect data. That's not what we do. What we actually do is something else. We only collect very few observations. These are the points where we measure. And then what we do is we use an interpolation function to calculate all the values in between. In a very brute and unscientific way, if this is 100 meters and this is 200 meters, we might assume that halfway it's 150 meters. We calculate a value. Now, we can only calculate a value when we know that that phenomenon is indeed continuous. And what we say then is that these continuous phenomena show spatial autocorrelation. And this is one of the main concepts in our domain, actually. It's also referred to as Tumblr's first law of geography. And it simply says that, locations that are close together are more likely to have similar values than locations that are further apart. It doesn't say they always have similar values. No, they are simply more likely to be similar. So if I sample here, let's say temperature in the courtyard, and I move to campus, my assumption is that the temperature there is very much like the temperature here. And if I have a weather station here and one in Deventer and one in another large city, via such an interpolation, I can actually generate a continuous surface by calculating all the values in between. But it only works for continuous phenomena that have spatial autocorrelation. And in your book, it will give you, for example, the sea surface temperature. If something changes very radically, it doesn't work. Because we don't have this continuous surface that we can actually model to calculate all the other values. Yeah? Okay? Oh, that's too fast. Now, let's say we want to store such a continuous phenomenon, or maybe even a discrete field. How can we do that? Now, the first way we can do that is via a regular tessellation. Now, regular tessellations, the definition, is a partitioning of space into mutually exclusive cells that together make up the complete study area. That's how your book describes it. It's actually like the tiles in your bathroom. What you do is you take your whole area and you cut them up into, well, equally shaped and sized areas. And what you do is, let's say this is this tiling of your bathroom, you attach a value to every tile. Now, in this case, maybe we are trying to represent land use. We have buildings, we have roads, we have fields. And what we do is we say, okay, this field, and this road, and this, well, I think this is the road and this is the building, right? So every single tile, every cell, we store one value. When we do this, it's very clear that this is a very good way of representing a value for your complete study area. What also becomes clear is that when we do this, we actually cut something that might be continuous into discrete areas. Yeah, we are storing one value for every single cell. Let's have a closer look at this. Now, a tessellation is also referred to as a raster. Yeah, in your living textbook, and you may have seen that I'm listing the concepts here all the time. In your living textbook, it will say a synonym is a raster. Yeah, a tessellation or a raster. Not the same as a grid. A grid is actually a set of regularly spaced points, and the value attached to this point only applies to this single location. But in a raster or a tessellation, the value attached to this cell applies to this complete area. So if the cell is 10 by 10 meters, that is one value per 100 square meters. But if the cell is 50 by 50 meters or 1 kilometer by 1 kilometer, yeah, that is much coarser. Okay, let's continue. How does that work with these values? So for every cell we store a value, but what if we're exactly on the boundary? I mean, when we are here, or here, or here, or here, what is the value there? Well, a lot of software actually has conventions saying that this value, in this case 3, is valid for this area plus the left and the lower boundary of that cell. Now, depending on the software you are using, this may vary. I was already indicating that if we store our data as a tessellation, what we're actually doing is we say only one value for this whole area, the area represented by that particular cell. So we create what we call a continuity gap. If this is temperature, we said, okay, the surface is changing gradually. And now we say this whole area is 18 degrees, this whole area is 19 degrees. So that is not really continuous. What we can do is we can say we make the cells smaller. Yeah? So on top you see larger cells, let's say 10 by 10 meters, and I go from 18 to 20. I can say make cells of 5 meters, and then I can go 18, 19, 20, 21. It's more continuous. That's a representation. However, instead of storing 1 cell, I now have to store 4. So there is a kind of a trade-off between how continuous you want to be and, well, the size of the file you need to store. So in this case, yeah, it depends on the features that you want to represent what a good cell size would be. You see here an integer value, 18, and an integer, 20. When something is continuous, you're representing temperature, of course, these are always floating point values, 18 point something, right? So, in fact, in this case, maybe the values of the representation could be changed, but this is to make it clear what we're talking about. Now, you might say, okay, even if I am storing 1 value per cell, if that point, the point for which that value is valid, is defined, maybe as the center of the cell or the left bottom corner of that cell, I can, in my software, do an on-the-fly interpolation and actually generate all the points in between. So what you could say is, yes, this is not a value which is the same for this complete area. However, this is the value at the center of that cell. And if you want to know other points, we will use that spatial autocorrelation, that Tobler's first law of geography, and then calculate the values in between. Technically speaking, that is possible. And that would be not a stored value, but a calculated one when needed, on the fly. However, a lot of software packages don't do this. Now you will go to a lot of practicals, you test it out, right? You zoom in to a single cell in a tessellation and you click and you figure out if it actually does this. Now, such a regular tessellation has advantages and disadvantages. Advantage, you exactly know what the partitioning is of space, the tiling, yeah, where your cells are. So if you start to calculate, this leads to very fast algorithms. If you need to, let's say, combine a lot of cells with the temperature for a certain location, and you need to calculate if there's a particular trend, you simply pick up for all these rasters that particular cell and you can calculate it. That is not difficult. That is the simplest calculation possible. So tessellations have great advantages. You can write underneath the advantages also, okay, if we collect data via remote sensing, an image is in fact a type of tessellation. So if we have an image, perform a classification on that, out will come naturally a tessellation. There are also big disadvantages. And there was a time when people were thinking, oh, these tessellations, they will disappear. It's a matter of time. The first one, they do not adapt to the spatial phenomenon that we want to represent. And the cell boundaries are both artificial and fixed and may not coincide with the actual phenomena. Let's have a look, right? Now, let's say we have a regular tessellation. And this is a crude drawing, but this is elevation. And here your terrain is completely flat. You still have to store values for this whole area. Yeah, it's a regular tessellation. It cuts your space into these equal squares or whatever shape you're using. So it doesn't adapt to your phenomenon. Even if nothing happens, you will store. If you have a house with a very irregular shape or a lake which has a very curved line, you will need to represent that as these tiles. Yeah? So these boundaries are fixed and artificial. They don't adjust to what you're representing. Now, the fact that you still have to store cell values, even if nothing happens, we can overcome. And I'm going to show you one example, in this case, the region Quadri. This is such a Quadri. What you see on the left-hand side is the area of your data layer. Let's say this is your map extent. And what you also notice is that this map extent is completely covered. Yeah, we have a value for everywhere in the study area. Yet, the cells are not equal in size anymore. We have larger areas represented by a single cell and smaller ones. So if you have certain areas where you have a lot of change, you can store more values, and in other areas you can store only one. How does this work? Well, what you do is you split up your area into 4 quadrants. Something like this. Yeah? So this is your area. You see the regular tessellation here, and you see an indication northwest, northeast, southeast, southwest. We cut this area into 4 quadrants. In this case, when we look at the values, and there are only a few, you see dark green here, light green and white. In this case, everything is dark green. As all the values are the same, if I only store one large cell, I'm not losing any information. This is the exact same, the same area, but then represented as the Quadri structure. You see here the northwest, that is the left top area, the northeast, the southeast, which is in fact this one, and the southwest. Now in this case, southeast has only one value, so we stop splitting this further and we store the output value. We go one level deeper, splitting the remaining sections again in quadrants. You see that we split this one, and that one further. You also see that this here has an extra layer, yeah, and that you have 4 units per square. If we look at the northwest, that is the left top one, what you see is that we have one that is finished in green, one that is finished in white, and 2 that needs to be further split up, here represented as circles. So we can continue this nesting, splitting these again, yeah, until everything is in fact green and we reached the end of our Quadri. So, when we move from a regular tessellation to an irregular one, like the Quadri, yeah, what we do is we have areas that are the same. We do not want to store every single cell, but we want to group them together. We split the regular tessellation in quadrants, see if there are multiple values. If there's still multiple values, we'll split them again. If there's a single value, we stop splitting. And that is what you would get. Okay? Now, a couple of remarks on this. Every time when I come back for the second lecture, one student comes to my desk and says, yeah, I've tested this out in ArcGIS. I don't see an irregular tessellation. That is because what you see on the screen is not what you save, what you store on your hard disk. What you see on your screen, even if you apply a quadtree, will be a regular tessellation, because it knows that all of these have the same value, so it can display this as if it were a regular tessellation. The second thing is, a quadtree is not the only, let's say, compression technique that you can apply. It is simply an example. And you are lucky, you only have to learn one. Yeah? So don't assume that if you check in ArcGIS, you'll find that it is applying region quadtrees. This is a nice one to show you that it can be done. Okay, then a couple of other issues. Quadtrees are adaptive because they apply spatial autocorrelation. They assume that there will be cells that are close together that have the same value. Yeah, so that is a way of assuming similarity, in fact. They provide a nested tessellation, so they split a quadrant again in a quadrant and a quadrant. And the square nodes at the same level have equal sizes, allowing for a fast and quick computation. And now, oops, sorry, I'm going back. What it knows is that let's assume a cell here is 100 by 100 meter. If it splits like this, it knows that this is a 4 by 4, so 400 by 400, 16 square meters at that level. It also knows that if it splits it at the next level, it will be a 200 by 200 split. And it knows that this level is 100 by 100. So it will quickly calculate, one of this level, 1, 2 at this level, and 1, 2, 3, 4, 5, 6, 7, 8 at this level. It multiplies that by the area, and it knows how much of this is, let's say, forest. Could be dark green, right? So that is, does it mean by, this allows fast computation. Okay? Yes?
Does that affect in any way the scale of the complete raster?
No, it doesn't. As I said, it's displaying it to you as a regular tessellation. A cell will still be, the lowest cell level will still be the same size, in this case 100 by 100. It is a compression technique to store these tessellations in a more efficient way. Yeah, but it doesn't directly affect the scale or resolution. Okay, so we have seen two types of tessellation. And we know that they store a value for every location in the study area. So they're very good for storing fields. However, we also had objects. And we sometimes want precise boundaries. We want to know exactly where a boundary is, not the best quality of a tessellation. So that's why there is a second group of computer representations, and we call them vector representations. Let's have a look. A tessellation or a raster does not explicitly store the georeference of every single cell. What it does is it stores one set of coordinates, one georeference, often for the lowest left corner. Because it knows that every cell has the same size, and it can look up the cell size, it's 50 by 50 meters, 100 by 100, right? It's in the header information. It can recreate the whole raster with only that information. It knows how many rows and columns, what the size of each cell is, and for one point it has a georeference. So it does not store the georeference of this cell. Vector representations, however, they explicitly store the georeference associated with the geographic phenomenon. So if we look at this area here, this point, the coordinates of this point are being stored. Of this point, of that point, of that point, of that point, of that point, they're all being stored. This makes it possible to actually make curved lines. Yeah? Define irregular shapes. Comes in very handy when you are building a cadastre, for example. Yeah? Or you have things like, roads, so to speak. Yeah? Making curves, etc. Vector representations. Okay. We discussed 4 types, and this is the first one, and it's called the triangulated irregular network. It's built from a set of measurements, and does anyone has a piece of paper that I can borrow? Or you may get it back in a different shape. Yeah, sure. Yeah, just tear it out. Thank you. Okay, this is my sheet. And this is how TINs, or triangulated irregular networks, work. I am now making a triangle. And I'm doing that to show you why triangles are so interesting to us. What we actually want to do is we want to define areas or shapes in a 3-dimensional space. And it says there it's built from a set of measurements. I can measure what the value is at this point. Let's say this is elevation and this is 100 meters. I do another measurement for this point, and let's say this was 100 meters, then this is 75. Now, if someone, user, holds the other anchor point, so this one, and we fix a measurement for that, we fix an area in 3-dimensional space. Actually, 3 points is the minimum number you require to define this area. That's why it's a triangulated data model. Okay, so let's look at this as if it were a map. We have measurements. You see them on the left. 30, 350, 1550, etc. Now, what I could do is I could hand out that picture there and ask you to connect these points so that this complete area is filled with triangles. The interesting thing then is that if I would collect all this back and we would have time to put it on the wall and would evaluate, you would see that there are many different ones. There are many different ways of connecting these points to form triangles, and we somehow need to come up with the best, or the one we are going to use. Now that's what you see here. Someone could have submitted this, and someone could have been submitting something like this. And the green dots are exactly at the same location. And what you see is the complete area is filled. So we have a value for every location in this study area, but the triangles are different. Now what we can do is we can say, okay, the preferred triangulation is in fact this one. And we call that a Delaunay triangulation. You can check if a triangulation is Delaunay by taking the anchor points of your triangle, drawing a circle through these anchor points, and checking if there are any other points in between the circle. If that is the case, your triangle is not the best one, not the most equal-sided triangle that you could have made. So what we can conclude there is that is not Delaunay. This one, however, is. And you see that for the edges, these triangles are very stretched, but in the middle, they are nice and equal-sided as possible. Okay, let's do some more thinking about triangulations. The interesting thing about triangulations, and there are a couple, is that if you define this triangle based on this measurement, and this measurement, you fix this area in three-dimensional space, you automatically also fix the slope of this area and the aspect, the orientation towards the sun. So when you are looking at triangulations in your software, it's very easy to say, okay, show me, as the coloring of the triangles, the slope values. Because it has that internally already calculated. Or in this case, you say, same triangulation, now show me the aspect, the orientation towards the sun. Is it north facing, east, south facing? And you get this picture. Now, why are triangulations of interest to us? They are adaptive to the phenomena that you are trying to represent. This is the triangulation, the same one as you saw in the previous picture. And what you see here is that you have areas with very, very, very small triangles, and there are also areas with very large ones. Here, not much is happening. So you collect very few points. In an area where you're very interested or where there's a lot of change, you collect a lot of points. So in this case, the data structure adjusts to the phenomena. Yeah? Okay. Now, is a tin a vector representation? Or is it perhaps a tessellation? Because it does create a tiling covering the complete area. Only these tiles are irregular in size, yeah, and shape. They may be more stretched or more compressed, your triangles. Now, why do we say that this is a vector representation? Because for every single anchor point, the georeference is stored. So for these points, I store the x and y coordinates. Question: do we store a value for that area? No. Huh? So what we do store is the anchor points, but not the area itself. That means that if someone asks you, what is the value at P? It doesn't go to the center point of this area to collect the value you have stored for this area. No, it will use these these anchor points to, on the fly, calculate the value of P. And you often see examples where you are asked to do that manually. So what do you think? What is the value at P? Any guess? What is the value at P?
Don't remember the values of the point.
Well, oh, sorry. Oh, well, I didn't intend to go that fast. Okay, these are the values of the points. 980, 1250, 1550. What do you think? Yeah, you saw already that I made categories, right? I don't want to exactly know, but any wild guesses? I have one vote. I don't know who voted what, right? So just take a wild guess. We have 4 brave people in this group. 10 now. 16, 17. These are the fast calculators. We have a reasonable group, right? When I hit the 40, I'm going to continue. Come on, 2 more. I don't think we'll make it. Yes, we do. Okay, closed. This is your result. So the most votes are in 1150 to 1200. Now, of more interest is how would you calculate the answer when this question would be in the exam, right? Okay, let's see if we have. What you would do is you would draw a line through point P, yeah, which would cut this edge. Now you can calculate where you are between these 2 points, in this case roughly 1115. Then you can measure, or guess in this case, how far you are between 1115 and 1550. You can see the point there. Well, your guess was quite good, right? Good job. You can perhaps not know exactly, but you can roughly estimate in this way where you would be. And if you want to, there is a detailed explanation ending up with 1157. Okay, when you're doing a triangulation, it's important where you pick your points. And the points, I mean the measurement points. What you will often see, if that is for elevation, you see that points are selected on the edge of your, not sure if this is actually running, but it's on the higher points, on the lower points, and in all the valleys of your landscape. Yeah? So if you pick these points carefully, you can come up with a pretty good representation. Okay. Now, in order to make a tin or a triangulated irregular network, we need to store points, right? And there is not much for me to say about storing points. You store an X and a Y coordinate, and perhaps, if this is 3D, you can store a height or a Z value. And that's it. So, not much to say about that. What if I want to store a line in a vector representation? For example, for our roads, we may want to store lines representing, for example, the road center line or the lane center lines, or maybe this is some other type of line that is of interest to you. What we do when we look at vector representations, all lines have a start point and an end point. So in principle, if we store 2 points and tell the software that these 2 points are connected, we can store a line. That would be the top picture. However, if we have a curved line, we will have to store internal nodes or vertices to create the shape. So the line still has a start and an end point, yeah? But it also has a number of other points you will need to store in order to represent the shape correctly. Not much more to say about this, actually. And by adding and adding and adding points, we can make nicer curved lines. That's obvious. And in your book, what you see is that different representation of the same feature are given, only changing the number of internal vertices that are being used to define this shape. What about areas? Well, when we want to represent an area, we have the habit of storing the boundary of that particular object. So what you see there in the top left corner is the principle of a boundary model. We store the parameter, the outline of each of these buildings. And if we look at the building layer, that will define our area. For every single area, we will need to store the nodes, the points that define the shape of that boundary. Now, there is one problem with that, and that is that if we define a boundary, maybe for this area here, and we define the boundary of the area next to it, if we store a boundary and another boundary, and this one is actually located here, what you see is that that part of the boundary is stored twice. And that's something we don't like. This is data redundancy. This is a potential problem, because if I accidentally pick up part of the boundary from the left polygon and move it, I'll have a gap. This is nasty business. Besides the fact that I'm storing things double, this is not what we want. And that is why we next time will look at topology. So tomorrow morning, we will look at topology and we'll look at topological data models to overcome the problem that we see here. Okay. So in summary, this is what we've done today. We looked at geographic phenomena. Are they objects, fields, discrete, continuous? We looked at data values, boundaries, scale, and resolution. And then we split computer representations into regular and irregular tessellations, rasters. And for the irregular tessellation, we saw the quadtree. And we said we have vector representations, which are either points, lines, polygons, or triangulated irregular networks, also called the TIN. Okay, now, when you look in your living textbook, what you will see is something like this. You see also the links between the concepts. Now you need to try to do two things. Understand what a concept means, how it works, and try to understand how concepts are linked together. Yeah? So, in your concept map, and I understood you looked at it yesterday already, you will see a representation like this one. This is our lecture of today. You see our geographic phenomena, computer representations split into vector representations, and the tessellations up there. You see that for the vector representations, we identify the lines, you see the points, you see the tin, right? Try to create a mental map of this lecture by simply putting all the concepts on a sheet, connect them, and see if you have a good overview. Yeah? And you can then go to the tool itself and check if your representation is correct. Make sure you do not miss out on anything. Okay, we'll see each other again tomorrow morning. My colleague, Tom Monk, is already waiting there for a demonstration on your software, ArcGIS. Tomorrow, 8:45, we will just continue, but then look at topology, topological data models, and also temporal, spatial temporal data modeling. Okay? I'll see you then. Okay. He wants to give you a 5-minute break. Okay. Ja, ik had ook een ding erbij. Ik ga hem even uitzetten. Is,